The story opens not with speculation, but with a measurement. In granite blocks from ancient Egypt, cylindrical drill holes and the cores extracted from them still exist. They are not impressions, not drawings, not stories passed down through generations. They are physical objects, preserved in stone, measurable today with calipers and microscopes. Along the surfaces of several of these cores runs a distinct pattern, a continuous helical groove that wraps around the cylinder as it descends. From that groove, one number emerges. By measuring the spacing between successive turns of the spiral and comparing it to the diameter of the core, engineers can calculate how far the drill advanced for each full rotation. The result is striking. The implied penetration rate is approximately 1/10 of an inch per revolution. That figure is not poetic. It is not symbolic. It is geometry, and it is the problem. Granite is not a forgiving material. It is an igneous rock, composed largely of quartz, one of the hardest common minerals on Earth, registering a 7 on the Mohs hardness scale. Quartz does not yield easily. It fractures, resists abrasion, and destroys cutting edges that are not sufficiently hard. For this reason, granite remains difficult to machine even today. In modern engineering, drilling granite is a slow and energy-intensive process. Industrial core drills use diamond-impregnated cutting edges, rigid steel bodies, precise alignment, and electric or hydraulic motors delivering consistent torque. Even under these conditions, penetration rates are measured in thousandths of an inch per revolution. A drill advancing too aggressively will stall, overheat, or shatter its cutting surface. 1/10 of an inch per revolution is not just optimistic, it is extreme. And yet, that is what the stone appears to record. The conventional understanding of ancient Egyptian stoneworking is well established. Archaeological evidence shows the use of copper tools, stone hammers, wooden mallets, and abrasive materials such as quartz sand. For drilling, hollow copper tubes were likely rotated by hand or with bow-driven mechanisms, while abrasive grit did the actual cutting. The copper did not slice the stone. It merely held the abrasive in place as the sand slowly ground the granite away. This method works. It has been demonstrated repeatedly. Holes can be drilled, cores can be extracted, but the process is slow, uneven, and sensitive to pressure, alignment, and fatigue. Abrasive drilling removes material incrementally, grain by grain, not in sweeping advances. Under this mechanism, a penetration rate of 1/10 of an inch per revolution is not just unlikely, it is physically implausible. The copper would deform long before sustaining such a feed rate. The abrasive grains would crush and scatter. The human operator would be unable to maintain the required downward force while also controlling rotation. The system would fail well before the stone yielded at that speed, and yet the grooves remain. They are not random scratches, they are not isolated marks. In several documented examples, the spiral maintains a relatively consistent pitch over multiple rotations. That consistency is what forces the question. Random abrasion does not usually produce regular geometry. Consistency implies control, and control implies a mechanism. This is the measurable engineering fact that does not align with the assumed technological capability. Either the grooves do not represent a true feed rate in the way modern engineers interpret them, or the process that produced them involved factors not fully accounted for in current models of ancient tooling. There is no third option. If the grooves are not diagnostic of rotation and feed, then their apparent regularity is misleading. Perhaps they are the result of overlapping abrasive marks, tool chatter, or post-depositional wear. In this view, the spiral is an illusion created by the way the surface has weathered or fractured over time. If the grooves are diagnostic, then the implications are narrower but sharper. The drilling process must have achieved a level of stability, pressure, and material removal efficiency that exceeds what simple copper and sand models predict. This does not require exotic explanations. It does not require lost civilizations or forbidden knowledge. It requires only that the physics be taken seriously. Granite does not care who drills it. It responds only to force, hardness, and motion. The debate exists because the stone preserves motion. Long before this discussion reached the internet or modern popular culture, the anomaly was quietly recorded by a man whose reputation rests on precision rather than imagination. In the late 19th century, the British Egyptologist Flinders Petrie conducted meticulous surveys of artifacts at Giza. Petrie was not searching for mysteries. He was cataloguing dimensions. He measured diameters, tapers, groove depths, and spacing. He noted, almost in passing, that the drill marks on certain granite cores cut more deeply through quartz than through feldspar. From a materials perspective, that observation is counterintuitive. Quartz is harder, feldspar is softer. Abrasive wear should preferentially remove the softer material, yet the opposite appeared to be true. Petrie did not speculate at length. He published the measurements and moved on. His role was not to explain everything, but to record faithfully what was there. For decades, those measurements attracted little attention. They did not fit neatly into existing narratives, but they also did not demand immediate revision of history. Stone drilling, after all, was considered a solved problem. Only when engineers began to look at the artifacts through the lens of machining theory did the numbers become uncomfortable. Feed rate is not a subjective concept. In manufacturing, it is one of the most fundamental parameters. It links rotation, material removal, and tool load. Exceed the allowable feed rate, and a tool fails. Reduce it too far, and efficiency collapses. Every material and cutting system has a range within which it operates. The ancient cores appear, at least on the surface, to lie far outside that range. This is where the story truly begins. Not with claims, but with constraints. Not with what we wish to be true, but with what the stone will allow. Because before any conclusion can be drawn, the grooves themselves must be interrogated, their geometry must be verified, their consistency must be tested, their relationship to tool motion must be established beyond visual impression. Are they continuous spirals or segmented marks? Do they maintain pitch over depth, or does the spacing vary subtly? Are they primary features of the drilling process, or secondary effects of abrasion and wear? Until those questions are answered, the contradiction remains suspended. The stone has spoken once, in numbers carved by motion and force. The challenge now is to listen carefully enough to understand what it is actually saying, rather than what we expect to hear. Subscribe to our channel if you are interested in this journey. In the late 19th century, a quiet shift occurred in archaeology, away from romantic description and toward disciplined measurement. At the center of that shift stood Flinders Petrie, a man less interested in myth than in millimeters. Petrie approached ancient objects the way an engineer approaches a machine, not asking what they meant, but what they were. When Petrie examined granite artifacts at Giza, he did not do so as a theorist searching for anomalies. He was conducting surveys. He brought rulers, calipers, plumb lines. He measured angles, diameters, tapers, and surface features with an attention to detail that was unusual for his time. His notebooks read less like travelogues and more like inspection reports. Among the objects he recorded were cylindrical cores extracted from drilled holes in granite. These were not decorative pieces. They were byproducts of a manufacturing process. To Petrie, that made them especially valuable, because waste material often preserves more information about a technique than finished surfaces do. He measured the diameter of the drill holes. He measured the diameter of the cores at multiple points along their length. He noted that some cores were slightly tapered, wider at one end than the other. He recorded the width and depth of surface markings, and he paid attention to the grooves. The grooves were not dramatic at first glance. They did not leap out as evidence of anything extraordinary. But when Petrie traced them carefully, he noticed that they wrapped around the core in a continuous pattern. The spacing between successive turns could be followed for multiple revolutions. It was regular enough to measure. More curious still was what happened when those grooves crossed different mineral grains. Granite is not uniform. It is a composite of quartz, feldspar, and mica, each with distinct mechanical properties. Quartz is hard and brittle. Feldspar is softer. Under abrasive action, feldspar should erode more readily. Yet Petrie observed the opposite. The grooves appeared deeper where they crossed quartz crystals and shallower where they crossed feldspar. This was not a philosophical claim. It was an observation made with the eye and confirmed with touch. Petrie noted it briefly, almost reluctantly, as if aware that it complicated the simplest explanation. From a material standpoint, this was unexpected. In abrasive wear, removal rate typically correlates inversely with hardness. Harder materials resist penetration, softer materials yield. The pattern Petrie recorded suggested either a different wear mechanism or an interaction more complex than loose abrasive grinding alone. Petrie did not attempt to resolve the discrepancy. That is important. He did not propose advanced machinery. He did not invoke lost techniques. He did not elevate the observation into a theory. He simply included it in his published measurements and moved on to the next artifact. In doing so, he demonstrated a discipline that is easy to underestimate. Petrie understood that measurement outlives explanation. Theories age quickly, numbers do not. At the time, there was little incentive to interrogate the data further. The prevailing understanding of Egyptian stoneworking was already sufficient to explain monument construction in broad terms. Copper tools and abrasives were known. Labor was abundant. Time was assumed to be effectively unlimited. Small inconsistencies did not threaten the overall model. As a result, Petrie's measurements settled into the background of the literature. They were cited, occasionally reproduced in diagrams, but rarely examined through the lens of mechanical engineering. Archaeology at the turn of the 20th century was not yet in conversation with machining science. Nearly a century passed. During that time, drilling technology evolved dramatically. Engineers developed quantitative models of cutting, grinding, and abrasion. Feed rate, torque, pressure, tool rigidity, and material hardness became standard variables. With those tools came a new ability to read marks in stone, not just as traces of effort, but as records of force and motion. When modern engineers returned to Petrie's data, they did not see curiosities. They saw parameters. The spacing of the grooves could be converted into feed per revolution. The taper of the cores could be related to tool wear or instability. The differential cutting through quartz and feldspar could be examined in terms of fracture mechanics rather than folklore. What Petrie had preserved unintentionally was a dataset, and datasets invite questions. If the grooves represented a rotating drill advancing steadily, what was the feed rate? If the feed rate was high, what force was required to sustain it? If that force exceeded the yield strength of copper or the endurance of human operators, what compensated for it? Alternatively, if the grooves did not represent steady feed, what process produced such regularity? Could abrasive grains trapped intermittently under a wobbling tube generate a pattern that mimicked a spiral? Under what conditions would that occur, and how often? These were not questions Petrie could have answered in his time, but he ensured that they could be asked later. There is a temptation, when revisiting historical measurements, to project intent backward, to imagine that Petrie knew he was uncovering a puzzle and deliberately left clues behind. That temptation should be resisted. Petrie was not planting seeds for future controversy. He was doing his job. That, paradoxically, is why his work matters. Because he did not argue, he did not distort. Because he did not speculate, he did not bias the record. The measurements stand apart from interpretation, available to anyone willing to engage them honestly. This is also why the issue cannot be dismissed as a modern misreading of old data. Petrie's numbers are not vague, they are specific. Diameters are given, groove spacing is illustrated. The physical artifacts still exist and can be remeasured. If the contradiction is illusory, it can be resolved experimentally. If it is real, it will persist under scrutiny. Either way, the path forward does not run through opinion. It runs through replication. Petrie moved on because archaeology at the time had other priorities: cataloging, chronology, typology. The engineering implications of tool marks were a niche concern. No one was asking how many thousandths of an inch per revolution an ancient drill could achieve. Today, that question no longer seems trivial, because once the numbers are taken seriously, they force a narrowing of possibilities. They demand either a reinterpretation of the marks themselves or a refinement of the assumed process that produced them. They do not allow both to remain vague. What exactly did those numbers encode? They encoded motion, pressure, constraint. They encoded the interaction between tool and stone, frozen at the moment the drill advanced, and the abrasive bit. And they encoded a challenge that would wait quietly in granite for generations, until someone trained to read machines learned to read stone the same way. To understand the contradiction, the baseline must be understood with absolute clarity. Copper tube drilling with loose abrasive is not cutting in the modern sense. It is grinding. The distinction matters because cutting and grinding obey different mechanical rules and leave different signatures behind. In a cutting process, a hard tool shears material away along a defined edge. In a grinding process, material is removed through countless microfractures caused by abrasive particles trapped between tool and workpiece. The tool does not define the geometry precisely, the abrasive does. Control is indirect and efficiency is low. In the ancient Egyptian context, the copper tube is not the active agent. Copper is far softer than granite. It cannot cut quartz. Instead, it serves as a carrier, a cylindrical container that traps abrasive grains against the stone, while rotation and downward pressure encourage those grains to fracture the surface. As drilling proceeds, the copper tube deforms. Its edge mushrooms outward, its circularity degrades. The abrasive grains break down, wash away, and must be replenished. The slurry thickens or thins depending on water content. None of these variables are tightly controlled. This is a fundamentally stochastic process. In experimental archaeology, this method has been reproduced many times. Researchers using copper tubes, quartz, sand, water, and human-powered rotation have demonstrated that granite can indeed be drilled. Holes can be formed. Cores can be extracted. The technique works.
But the rate matters.
When penetration rates are measured, they are consistently low. Removing even a few millimeters of granite often requires hours of continuous effort. The drill advances incrementally, sometimes unevenly, sometimes stalling altogether as abrasives dull or pressure fluctuates. This slow progress is not a failure of the experiment. It is exactly what material physics predicts. Granite resists abrasion. Quartz grains fracture and lose effectiveness. Copper edges yield under load. Without a rigid system to maintain pressure and alignment, energy is dissipated rather than concentrated. The process grinds forward, but reluctantly. Because of this, the surface signature left behind is characteristically irregular. Instead of a single, continuous groove, the interior walls of experimentally drilled holes tend to show overlapping scratch patterns. Some marks are horizontal, others diagonal. Some deepen briefly and then fade. The surface reads like noise rather than signal. When a copper tube wobbles even slightly, as hand-powered tools inevitably do, the abrasive action shifts around the circumference. One side bites more deeply for a moment, then releases. The result is a patchwork of wear, not a disciplined geometry. This matters because geometry is information. A consistent helical groove implies that, over multiple rotations, the tool advanced downward by roughly the same amount each time. It implies that pressure and alignment were maintained with relative stability. It implies that the interaction between tool, abrasive, and stone did not reset randomly every few seconds. That is not how loose abrasive grinding normally behaves. In grinding systems where spirals do appear, such as modern lapping or honing machines, the geometry is enforced by rigid constraints. The tool path is fixed. Feed is controlled mechanically. Abrasive motion is predictable because the system is constrained. Remove those constraints and the spiral dissolves. This is why the ancient cores provoke attention, not because abrasive drilling cannot explain drilling in principle, but because the specific surface patterns do not align neatly with what uncontrolled abrasive grinding typically produces. It is tempting at this point to assume that any spiral-like appearance must indicate advanced tooling. That temptation must be resisted. Abrasive processes can produce surprising regularities under certain conditions. Grain size distribution, slurry viscosity, and incidental tool bias can sometimes align marks in ways that mimic structure, but mimicry has limits. If a spiral is merely apparent, an emergent pattern from chaotic abrasion, then its pitch should vary unpredictably. Groove depth should fluctuate, the pattern should break down over length, consistency should be accidental and short-lived. In several ancient cores, however, the spacing between turns remains relatively uniform over multiple rotations. That does not prove intentional feed, but it does demand explanation. Another factor must be considered: pressure. In abrasive drilling, penetration rate scales strongly with normal force. Press harder, and the abrasive grains fracture the surface more aggressively. But pressure is constrained by the weakest element in the system. In this case, that element is copper. Copper deforms plastically under relatively low stress. Increase pressure too much and the tube edge flares outward, reducing contact efficiency. The abrasive escapes. Cutting slows. Push harder still, and the tube collapses or jams. This self-limiting behavior is why abrasive drilling remains slow even when effort is increased. Human-powered systems also introduce variability. Muscle force fluctuates, fatigue sets in. Maintaining steady downward load while also rotating a drill smoothly is difficult over long periods. Minor changes in posture or grip alter tool alignment, introducing wobble and uneven wear. All of this conspires against consistency. So when a surface pattern suggests steady feed, the immediate question is not how impressive it looks, but how stable the system must have been to produce it. This is where the contradiction sharpens. If the ancient process was truly copper tube drilling with loose abrasive, then either the grooves are being misinterpreted or the process behaved in a way not fully captured by modern experimental replication. There is no need to assume missing technologies. There is, however, a need to account for every variable honestly. Could abrasive grains have been larger, harder, or more angular than those typically used in experiments? Possibly. Could the slurry have been optimized through experience, producing more aggressive wear? Perhaps. Could the drill have been guided more rigidly than often assumed, reducing wobble? That remains an open question. What cannot be ignored is that grinding processes leave statistical fingerprints. They produce distributions, not lines. They average out over time. Regularity, when it appears, usually reflects constraint. The ancient cores sit uncomfortably at the boundary between these categories. They look too regular to be dismissed outright and too demanding to accept without scrutiny. Understanding what abrasive drilling actually does is essential precisely because it narrows the field. It tells us what should be expected, what is typical, and what would require special explanation. The stone does not argue, it records, and once the baseline is understood, the next step is unavoidable. The geometry itself must be examined more closely to determine whether it truly encodes a feed rate, or whether the eye is being deceived by pattern where none was intended. A true spiral is not decorative, it is diagnostic. In engineering, a spiral is not an aesthetic flourish left behind by chance. It is the geometric consequence of a very specific relationship between motion and constraint. When a tool rotates while advancing steadily along an axis, the path traced at the interface becomes helical. Each revolution corresponds to a fixed increment of linear progress. Change the feed, and the pitch changes. Interrupt the motion, and the spiral breaks. This is why spirals are so useful to engineers. They encode behavior. A helical groove implies four things simultaneously: continuous rotation, continuous downward feed, stable tool geometry, and controlled pressure. Remove any one of these, and the spiral collapses into noise. If rotation is intermittent, the groove becomes segmented. If feed varies, the pitch fluctuates. If the tool wobbles, the path loses coherence. If pressure is inconsistent, the depth oscillates. A clean spiral is, in effect, a signature of mechanical discipline. In machining, this relationship is formalized. Feed rate per revolution is a primary variable, calculated simply by dividing linear advance by rotational count. If a drill advances 1 millimeter per turn, the pitch of the resulting helix is 1 millimeter. There is no interpretation involved. Geometry does the accounting. This is why the grooves on certain ancient granite cores attract attention, because when their pitch is measured, carefully, conservatively, the implied feed rate is large, not marginally large, uncomfortably large. The calculation itself is straightforward. Measure the vertical distance between successive turns of the groove. Measure the circumference of the core. One full rotation corresponds to one full wrap around the circumference. The vertical spacing between wraps is the advance per revolution. When that spacing approaches 1/10 of an inch, the implication is unavoidable. The drill advanced that far each time it turned once. In soft materials, such a feed rate would be unremarkable. In wood, it would be trivial. In aluminum, aggressive but manageable. In granite, it is extraordinary. Granite does not shear cleanly, it fractures. It resists penetration until stress thresholds are exceeded, then fails abruptly. Managing that behavior requires either extreme hardness at the cutting edge or extremely low feed rates. Modern drills accept this reality. They move slowly, deliberately, allowing countless microfractures to accumulate without catastrophic failure. A feed rate of 1/10 of an inch per revolution pushes directly against that constraint. This is why the geometry matters so much, because if the groove truly records steady rotation and feed, then the process that produced it must have been mechanically robust, well-constrained, and capable of sustaining high loads without collapsing. But geometry can deceive. Not every spiral-like pattern is a true helix. Surfaces can suggest order where none exists. Overlapping scratches can align by chance. Abrasive grains can preferentially follow weak paths in the material, creating apparent continuity that breaks down under closer inspection. The eye is particularly susceptible to this kind of illusion. Humans are pattern recognition machines. We connect lines instinctively. We impose structure even when the underlying process is random. This is why the question must be asked carefully. Are these grooves truly spiral in the mechanical sense, or are they something else entirely? To answer that, one must look beyond appearance and examine consistency. A genuine helix maintains pitch over length. The spacing between turns does not drift. Minor variations may occur, but the overall advance per revolution remains stable. In contrast, an emergent pattern from abrasive chaos will show irregular spacing, variable depth, and interruptions. Some ancient cores appear to show the former, others do not. This ambiguity is central to the debate. Critics argue that the grooves are being overinterpreted, that what looks like a spiral is actually a composite of many partial marks produced as the abrasive slurry redistributed itself during drilling. In this view, the drill did not advance smoothly. It juddered, stalled, and re-engaged repeatedly, leaving behind a confusing palimpsest of scratches. Supporters of the feed rate interpretation counter that, at least in certain examples, the groove spacing is too regular to be dismissed as coincidence. They point to stretches where multiple turns can be traced with minimal variation, suggesting a stable relationship between rotation and advance. Neither position can be resolved by rhetoric. It is a geometric question. One useful test is continuity. Does the groove wrap fully around the core without interruption? Does it maintain depth across mineral boundaries? Does it persist even where the core tapers slightly? Each of these features strengthens the case for a true helix. Another test is correlation. If the groove pitch corresponds consistently to the taper of the core, That implies a causal relationship between tool wear and feed. Random abrasion would not produce such correlation.
Yet even here, caution is required. Abrasive processes can, under certain conditions, self-organize. If a drill consistently leans in one direction due to operator bias, a pseudo-helical wear pattern could emerge. Over time, that bias might be reinforced rather than corrected.
The problem, then, is not deciding whether a spiral exists, but deciding what kind of spiral it is. In modern machining, spirals are deliberate. In grinding, they are usually artifacts of constraint. In chaotic abrasion, they are rare and fragile. Which category do the ancient grooves belong to? This is not a semantic question. It determines whether the feed rate calculation is meaningful or misleading. If the grooves do not encode rotation and feed, then the implied penetration rate evaporates. The contradiction dissolves, not because the stone changes, but because our reading of it does. But if the grooves do encode that relationship, then the numbers must be faced. The granite does not allow compromise, it does not negotiate, its fracture behavior is well understood, its hardness is measurable. If a process exceeded known limits, it did so physically, not metaphorically. This is why the debate remains unresolved, because the geometry sits at the threshold between signal and illusion. To move forward, the spiral itself must be interrogated with the same discipline Petrie applied to diameter and depth. Not admired, not dismissed. Measured, quantified, and tested against known mechanisms. Only then can we determine whether the stone is recording an impossible feed rate, or warning us that we have misunderstood the language it uses to speak. What do you think about this? Share your thoughts in the comments section. Close examination of the cores complicates the picture rather than clarifying it. When these granite cylinders are measured carefully, they do not present themselves as idealized machine products. They show taper. They show asymmetry. Some narrow slightly along their length, others widen. The circular cross-section drifts subtly, betraying moments when the tool was not perfectly centered. Groove depth fluctuates, sometimes fading, sometimes biting more deeply into the stone. These are not the marks of a rigid modern machine. They look, in many respects, exactly like what one would expect from a hand-driven process. Tool wander is visible. Pressure was not perfectly uniform. The drill did not advance as a flawless piston along a single axis. It moved, corrected, drifted, and re-centered itself again and again. Critics of the high feed rate interpretation point to these features as decisive. Taper, they argue, is the signature of abrasive drilling. As the copper tube wears, its cutting edge spreads or collapses unevenly. Abrasive grains accumulate more on one side than the other. The hole widens or narrows accordingly. None of this requires mechanical precision. Asymmetry, too, fits comfortably within this framework. A human operator cannot maintain perfect alignment over long periods. Even slight shifts in posture or grip introduce lateral forces. Over time, these forces carve a subtly irregular path. Groove depth variation strengthens the case further. Abrasive action is episodic. Fresh grains cut more aggressively. Worn grains polish rather than penetrate. Slurry viscosity changes. Water content fluctuates. Pressure rises and falls with fatigue. All of this produces uneven wear. Taken together, these features appear to argue against the idea of controlled mechanical feed, and yet they do not dissolve the problem. Because within this imperfect geometry, something persists. In several documented cores, the spacing between successive turns of the groove remains surprisingly consistent over multiple rotations. Not perfectly uniform, but close enough that the eye can follow the path continuously. The groove does not fragment into isolated scratches. It does not wander randomly around the circumference. It maintains a rhythm. That rhythm is what resists easy explanation. Consistency is not an all-or-nothing property. A system can be messy and still constrained. Modern machines leave imperfections too. Bearings wear, tools chatter, heat causes expansion. Yet beneath those deviations, the governing motion remains legible. The question then is not whether the ancient cores are perfect, but whether they are consistent enough to encode a process.
If the groove spacing were entirely random, the feed rate interpretation would collapse immediately. Random abrasion cannot be reverse engineered into deliberate motion. But when spacing repeats, even approximately, the possibility of an underlying constraint reasserts itself. This is where the hand-driven abrasive model is tested most severely. In such a system, what enforces consistency?
Human operators can maintain rhythm, but not precision. A bow drill introduces oscillatory rotation, not continuous spin. Each stroke accelerates, decelerates, and reverses direction. Downward pressure fluctuates with muscle tension and fatigue. Alignment drifts as the operator adjusts balance. Under these conditions, advance per rotation should vary significantly. One stroke might cut slightly more, the next slightly less. Over time, these variations should accumulate into irregular spacing. Yet the stone sometimes suggests otherwise. One possible explanation is bias. If the operator unconsciously favors one direction of rotation or applies pressure more effectively during one phase of motion, the drill could advance preferentially during that phase. Over many cycles, this bias might imprint a quasi-regular pattern, but such bias would still be modulated by fatigue, abrasive breakdown, and tool deformation. Maintaining similar advance over multiple full rotations would be difficult. Another possibility lies in constraint external to the operator. A guide of some kind, wooden, stone, or composite, could stabilize the drill laterally, reducing wobble and enforcing a more repeatable path. This would not require advanced machinery, only careful setup. Guidance, however, does not solve the feed problem. It may explain alignment, but not penetration rate. Consistency in spacing still implies consistency in advance. Pressure remains the critical variable. To advance a drill through granite by a significant amount per rotation requires force. Not momentary force, but sustained force. If that force fluctuates wildly, advance fluctuates with it. Consistency implies that force was regulated somehow, even if imperfectly. In hand-driven systems, regulation is limited. Muscles are poor governors. They overshoot and undershoot. They tire. They compensate late. This is why modern machines use weights, springs, and actuators to maintain feed. The goal is not power, but regularity. The ancient cores sit in an uncomfortable middle ground. They show signs of irregularity consistent with handwork, yet they also show traces of regularity that handwork struggles to maintain. Neither side of the debate can ignore the other. Those who emphasize the imperfections must explain why the groove spacing does not dissolve into chaos. Those who emphasize the regularity must explain why the cores are not more precise. The stone refuses to take a side. It records both instability and order, sometimes within the same centimeter of surface. It suggests a process that was neither crude nor fully mechanized, neither purely random nor rigidly controlled. This is why consistency is the heart of the problem. Not because it proves anything outright, but because it narrows the field of plausible explanations. It demands a mechanism that can tolerate imperfection while still enforcing repetition. It demands a system that allows drift without losing rhythm. Such systems exist. They are common in transitional technologies where human effort is augmented by simple mechanical constraints. They do not require motors or hardened steel, but they do require intentional design. Whether such design was present here remains an open question. What cannot be dismissed is that the stone preserves evidence of repetition in a context where repetition is mechanically expensive. The cores do not shout, they whisper. They do not declare impossibility. They suggest tension between what should be expected and what appears to have occurred. And that tension does not vanish when the imperfections are acknowledged. It sharpens. Penetration rate is never just about motion. It is about force. Rotation alone does nothing to granite. A drill can spin endlessly against quartz without removing a single grain unless sufficient normal force presses abrasive into the surface. Every act of material removal begins with pressure. Without it, there is only friction and heat, not fracture. This is the variable that rarely announces itself in surface patterns, yet governs everything they record. In abrasive drilling, pressure performs two roles simultaneously. It embeds abrasive grains into the softer tool material, copper in this case, and it drives those grains hard enough against the stone to exceed the fracture strength of the mineral. Both steps are essential. Too little pressure and the grains skid uselessly. Too much and the system fails. Quartz is unforgiving in this regard. Its hardness is only part of the story. More important is its fracture toughness. Quartz does not smear or plastically deform. It resists until stress concentrates, then it breaks abruptly. To make that happen repeatedly, at speed, requires force that must be applied steadily and continuously. This is where the implied feed rates become problematic. A feed rate of 1/10 of an inch per revolution in granite implies that, with each turn, abrasive grains penetrated deeply enough to remove a substantial volume of material. That cannot occur through light contact. It requires sustained compressive load at the tool-stone interface. In modern systems, that load is supplied mechanically. Drill presses use weighted spindles. Industrial coring machines rely on hydraulic rams or precisely calibrated springs. The operator's role is supervisory, not muscular. The machine supplies the pressure because humans cannot. In a hand-powered bow drill, the situation is reversed. The human supplies everything: rotation, alignment, and downward force. There is no passive regulator. Pressure fluctuates with posture, leverage, and fatigue. Even at peak effort, the force that can be applied through the arms and shoulders is limited, and more importantly, it cannot be maintained indefinitely. Short bursts of high pressure are possible. Sustained high pressure is not. This limitation is not theoretical. It is biomechanical. Muscles fatigue, grip weakens. Micro-adjustments become less precise. As effort increases, control decreases. In drilling, loss of control translates directly into wobble, loss of abrasive contact, and reduced cutting efficiency. Even if a human operator could briefly generate the force needed to drive abrasive aggressively into quartz, maintaining that force while also rotating a tool smoothly for multiple revolutions would be extraordinarily difficult. And then there is the tool itself. Copper is ductile. Under increasing load, it deforms plastically rather than elastically. Its yield strength is low compared to the stresses required to fracture quartz at high rates. Press too hard, and the cutting edge mushrooms outward, spreading the load and reducing contact pressure. The very act of pushing harder makes the process less effective. This self-limiting behavior is well documented in experimental archaeology. Attempts to increase penetration rate by applying more force quickly reach diminishing returns. Beyond a certain point, more effort does not produce more cutting. It produces deformation, slippage, and tool failure. The abrasive grains introduce another constraint. Quartz sand fractures under load. As pressure increases, grains shatter into finer particles. Finer particles polish rather than cut. Aggressive pressure accelerates this breakdown, requiring constant replenishment of abrasive just to maintain baseline effectiveness. In other words, the system resists being forced. This resistance is why abrasive drilling progresses slowly under realistic conditions. It is not a matter of inefficiency, it is a matter of physics enforcing limits. So when a surface pattern suggests rapid advance, pressure becomes the central question. Where did it come from? One could imagine multiple operators applying force together, distributing effort. This might increase total load, but it introduces coordination problems. Maintaining alignment and consistent feed with multiple people is more difficult, not less. Force vectors shift, stability suffers. One could imagine weights suspended above the drill, providing passive downward force. This would reduce reliance on muscle and introduce a more constant load. Such a setup is mechanically plausible and does not require advanced technology. But it would leave its own constraints. The weight must be guided. The drill must be constrained laterally to prevent buckling. The system becomes more complex, not less. Crucially, there is little direct archaeological evidence for such weighted drilling rigs in ancient Egypt. That absence does not prove they did not exist, but it does limit how confidently they can be invoked. Even if such a system were used, the question of magnitude remains. How much pressure is required to sustain the implied feed rates? And how does that pressure compare to what copper tubes and abrasive systems can tolerate before failing? These are not philosophical questions. They can be estimated. Modern machining data provides approximate values for contact pressures required to fracture quartz under abrasive action. While exact numbers depend on grain size and geometry, the orders of magnitude are known. When those pressures are translated into required force over the contact area of a copper tube edge, the resulting loads are substantial enough that copper deformation becomes a dominant failure mode. This brings the discussion back to the stone itself. The cores show evidence of tool wear and instability. They do not show catastrophic collapse. The process, whatever it was, operated within material limits. That suggests one of two possibilities. Either the feed rate implied by the grooves is being overestimated, or the pressure was applied in a way that avoided overwhelming the tool, perhaps intermittently, perhaps through a mechanism that redistributed load more effectively than simple hand pressure. Intermittent pressure could, in theory, allow higher momentary penetration without sustained overload. But intermittent pressure tends to produce irregular advance, not consistent spacing. Once again, consistency intrudes. Pressure, unlike rotation, leaves no obvious trace by itself. It must be inferred indirectly from penetration depth, from material response, from tool wear patterns. It is the silent variable, but it governs everything. If the pressure was low, the feed rate must have been low. If the feed rate was high, the pressure must have been high. Both cannot be true simultaneously. The stone does not tell us how the pressure was applied. It tells us only that material was removed in a way that appears, at least in places, to exceed what low, fluctuating pressure would allow. Where did the pressure come from? That question cannot be answered by appealing to rotation, geometry, or abrasion alone. It demands a closer look at the mechanics of assistance, at whether the process relied solely on human effort, or whether simple but powerful aids were quietly doing more work than the hands that guided them. When a claim rests on stone rather than text, the only honest response is replication. Over the past several decades, engineers and experimental archaeologists have attempted to reproduce ancient Egyptian drilling using materials, tools, and power sources consistent with what is known from the archaeological record. Copper tubes were fabricated. Quartz sand was selected as abrasive. Water was added to form slurry. Human-powered rotation was applied by hand, by bow, and by simple rigs designed to approximate ancient conditions. The outcome of these experiments is not in dispute. Granite can be drilled, cylindrical holes can be produced, cores can be extracted. The basic feasibility of the technique has been demonstrated repeatedly. What has not been reproduced is the geometry. Specifically, the pitch of the grooves left behind by these experimental drills does not approach what is observed on certain ancient cores. The marks are present, but they are shallow, irregular, and inconsistent in spacing. They break and restart. They drift. They overlap. They do not form a stable helical pattern over multiple rotations. In other words, replication succeeds in principle but fails in parameter. This distinction matters. A method that works in principle establishes plausibility. A method that reproduces parameters establishes equivalence. The former answers whether something could have been done at all. The latter answers whether it was done in the way the evidence suggests. So far, equivalence has not been achieved. When experimenters attempt to increase penetration rate, the same constraints appear again and again. Applying more pressure deforms the copper tube. Abrasive grains fracture and lose effectiveness. Alignment deteriorates. Instead of cutting faster, the system becomes less stable. Increasing rotation speed introduces new problems. Friction heats the slurry. Abrasives wash out of the cutting zone. The tube skates rather than bites. Control is lost. In some cases, experimenters have succeeded in producing more regular marks by introducing greater constraint. Rigid guides reduce wobble. Fixed rigs enforce alignment. Under these conditions, the surface patterns become cleaner. But even then, the feed rate remains low. The geometry improves, but the scale does not. When modern machinery is introduced, the picture changes immediately. Electric drills with rigid spindles, constant feed mechanisms, and hardened cutting surfaces can produce clean, consistent spirals in granite. The pitch can be adjusted at will. Increase feed and the groove steepens, decrease it and the spiral tightens. This is not surprising. Modern machines are designed to overcome exactly the limitations that constrain hand-driven systems. What is telling is that the ancient-like geometry appears only when those modern advantages are present. This does not prove that ancient tools were inadequate. It proves that the simplest reconstructions of those tools are inadequate to reproduce all observed features. One response to this mismatch is to question the experiments themselves. Perhaps the abrasive grain size was wrong. Perhaps the copper alloy was not historically accurate. Perhaps the operators lacked the skill of ancient craftsmen. Perhaps subtle techniques, learned through experience, are missing. All of these are possible. Craft knowledge is often tacit. It is transmitted through practice, not instruction. Ancient artisans may have understood how to tune slurry composition, pressure and motion in ways that modern experimenters have not rediscovered. But here again, the numbers impose discipline. Even generous adjustments to abrasive efficiency do not close the gap between thousandths of an inch per revolution and tenths. Even highly skilled hands remain limited by muscle endurance and material yield. Skill can optimize within constraints. It cannot eliminate them. Another response is to argue that the ancient examples themselves are being misread, that the groove pitch has been overestimated, that erosion has exaggerated spacing, that selective attention has focused on outliers rather than typical cases. This critique has merit. Not all ancient cores show dramatic spirals. Many are ambiguous. Some appear entirely consistent with slow abrasive drilling. The dataset is small, and selection bias is a real risk. But replication does not need to match every example to be instructive. It needs only to show that the proposed mechanism can, under some conditions, reproduce the observed features. So far, that threshold has not been crossed. This leaves an uncomfortable gap. The method works, but not at the observed scale. The principle is sound, but the parameters are misaligned. In engineering, such gaps usually indicate one of three things. Either a variable has been misunderstood, a constraint has been underestimated, or the interpretation of the evidence is flawed. The first possibility suggests that something about the ancient process is missing from modern reconstructions. Not a miraculous technology, but a mechanical aid, a configuration, or a sequence of operations that alters performance significantly without leaving obvious traces. The second possibility suggests that the limits of hand-driven abrasive drilling are being misjudged. Perhaps under certain conditions, rare, difficult to sustain but real, higher feed rates are achievable than modern intuition allows. The third possibility suggests that the grooves are not what they seem, that they do not record steady feed per revolution, but something more complex and less direct. Replication alone cannot decide between these options, but it can constrain them. What replication has shown clearly is that ordinary copper tubes, loose abrasives, and human power do not naturally produce clean, high-pitched spirals in granite. When such spirals appear, something else is at work. Whether that something else is mechanical assistance, unusual constraint, or misinterpretation remains unresolved. What is resolved is that the problem cannot be dismissed by asserting that the Egyptians could do it. The details matter. In science and engineering, the devil is not in the unknown, it is in the mismatch. The ancient method works, but not the way it appears to have worked. That discrepancy is small in words, but large in implication. And until it is resolved, the cores remain what they have always been. Not proof of impossibility, but evidence that our simplest models may be incomplete. Granite is not uniform. It is a composite of minerals, each with its own mechanical behavior. Quartz, hard and brittle, resists abrasion until stress concentrates, then fractures suddenly. Feldspar, softer and more brittle in different ways, yields more readily. Mica layers cleave along planes, introducing irregularities into the grain matrix. To a casual observer, granite may appear consistent, but under stress it behaves unpredictably. Its surface tells a story of chaos constrained by physics. Some engineers and archaeologists have argued that this heterogeneity could explain the apparent contradiction. Perhaps the grooves that suggest high feed rates are not records of deliberate, continuous motion at all. Perhaps they are the emergent result of localized fractures. When quartz yields under concentrated pressure, microspalls detach. When multiple spalls form along a similar path, a groove emerges. Repeat this process thousands of times, and one can imagine a pattern resembling a spiral forming incidentally. The irregularity of the stone itself could bias the abrasive grains, channeling their motion in ways that mimic controlled rotation. Experiments support this to a limited degree. When copper tubes with abrasive slurry are pressed into granite, the grains do not remove material evenly. They fracture quartz and feldspar in unpredictable ways. Occasionally, one side of a grain will catch more aggressively. Sometimes the slurry channels along a weak plane. Small variations in pressure, combined with the stone's heterogeneous structure, can produce grooves that appear coherent over short lengths. Viewed without precise measurement, these can resemble mechanically controlled feed. But there is a catch. Random processes, by definition, produce distributions rather than constants. The more consistent the spacing and depth, the less likely it is to result from chance. A groove formed purely by stochastic microfractures would rarely maintain uniform pitch over multiple rotations. Deviations accumulate. Minor inconsistencies in pressure, abrasive placement, or stone composition manifest as irregularities in spacing, depth, and alignment. Over the length of an Egyptian core spanning tens of centimeters, the odds that random fracture alone produces a near-regular helical pattern diminish sharply. Material science therefore pushes back against claims that randomness alone explains the evidence. The microfractures induced by abrasive grains are constrained by physics, yes, but constraints in this context rarely produce near-perfect linearity. Statistical analysis of experimental drilling shows that even under tightly controlled repeated conditions, pitch variation exceeds what is observed in some ancient cores. Uniformity does not emerge naturally from chaos. Granite's heterogeneity complicates matters further. In one region, the quartz may be tightly interlocked, requiring more force to fracture. Adjacent feldspar grains yield more easily. Mica sheets introduce planes of weakness that can deflect abrasive action. These variations should produce a signature of irregularity, asymmetrical grooves, shifts in depth, inconsistent curvature. In some ancient cores, these expected deviations are present, but in others, the grooves maintain remarkably steady pitch and depth, despite the heterogeneous material. Here, the argument for stochastic formation weakens. Advocates of material science explanations also point to the behavior of abrasives under high stress. Abrasive grains fracture unpredictably, creating sharp edges that can bite more aggressively into certain mineral phases. This can produce momentary accelerations in material removal. These bursts might, in theory, mimic higher feed rates, but they remain transient. Over multiple rotations, the effect averages out. The sustained uniform feed implied by some groove measurements does not emerge from intermittent grain fractures alone. The statistical expectation of randomness favors irregularity, not the stable rhythm observed in certain cores. There is also the consideration of operator feedback. In a hand-driven system, the human eye and hand respond to resistance. If a grain catches and produces an unexpected bite, the operator naturally adjusts pressure and rotation. These micro-corrections further disrupt any emergent uniformity. In effect, randomness is damped by human intervention. While this could smooth some variations, it cannot enforce precise, repeated spacing without some mechanical aid or guiding principle. Material behavior alone does not provide that feedback loop. Finally, experimental replications with controlled abrasives show that even when stone heterogeneity is leveraged deliberately, stochastic variation dominates. High-speed photography and micrometer analysis reveal that individual fractures are inconsistent in depth, orientation, and spacing. Only when rigid guides, constant feed, or external mechanical constraints are introduced do the patterns stabilize. This suggests that granite's natural properties alone are insufficient to explain the coherence of the helical grooves seen on some ancient cores. Material science, then, narrows the argument. It offers an explanation for certain irregular features, variable depth, localized chipping, asymmetry. It explains why copper tube drilling can eventually remove a core without catastrophic failure. It explains many of the minor inconsistencies that appear in experimental reproductions, but it cannot fully account for the regularity that the pitch measurements imply. Random microfractures and localized bite do not encode stable, repeatable feed. Statistical distributions do not masquerade convincingly as linear, helical advance over tens of centimeters. This is why the problem persists. Even after accounting for material heterogeneity, abrasive behavior, and stochastic fracture, the cores retain a feature that seems deliberately mechanical. A consistent groove spacing, a rhythm, a pattern that encodes feed per rotation. If randomness were sufficient, replication would achieve both the baseline and the parameter simultaneously. It does not. Granite's resistance, in combination with the stochastic nature of abrasive cutting, therefore reinforces the paradox rather than dissolving it. The stone can explain why some features vary, why taper occurs, and why irregular scratches appear. It cannot, however, explain why certain cores appear to exhibit coherence where statistical chance would predict chaos. Uniformity in this context is not accidental. It is constrained by something beyond mere material behavior. In essence, material science provides both illumination and limitation. It illuminates the difficulties of hand-driven abrasive drilling, clarifies why irregular features appear, and shows the physical constraints imposed by granite itself. But it also limits the explanatory power of stochastic models. Consistency over length, depth, and rotation remains anomalous under purely random processes. The physics of fracture, abrasion, and copper deformation set boundaries that randomness cannot comfortably cross. Granite fractures unpredictably. Abrasives bite variably. Human operators fluctuate in force and alignment, and yet in some cores, the spiral persists with surprising steadiness. Material science can explain why deviation occurs, but it cannot fully account for the observed regularity. Randomness rarely produces uniformity, and that is precisely why the contradiction endures. The cores are neither fully explained by tool limits nor by material behavior alone. Somewhere between the stochastic and the controlled, the evidence waits, unresolved. Several of the ancient cores stand out not for their size or depth, but for their shape. Viewed from above, the cross-sections approach near perfect circles. Viewed along the length, the diameter remains surprisingly consistent, tapering only slightly, if at all. The walls do not fluctuate dramatically from side to side. Groove paths follow the same curvature around the axis. These are not the imperfections expected from a purely hand-driven, loose abrasive system. They are evidence of radial consistency, a uniformity in dimension that is difficult to achieve without some form of tool stabilization. Radial symmetry is deceptively simple in appearance, but mechanically demanding in practice. When a tool rotates freely under human power, multiple factors introduce deviation. The hand cannot apply exactly equal lateral pressure in all directions. Muscular fatigue subtly shifts the angle of rotation. The copper tube itself flexes and yields, spreading unevenly against the stone. Abrasive grains shift unpredictably, following the path of least resistance. Each of these contributes to wobble, a tool path that deviates from a perfect cylinder. Over many rotations, the wobble amplifies, producing ellipticity or irregular walls. Yet in the cores under discussion, such deviations are minimal. Circularity is maintained over lengths of tens of centimeters, even as the material being removed is granite, a composite rock with significant hardness and brittleness. This observation alone suggests that some mechanism, however simple, constrained lateral movement of the drill. The tool must have been guided or supported in a way that limited deflection. Otherwise, the natural flexibility of copper and the variability of hand-applied force would have produced elliptical cores, lopsided walls, or broken spirals. Experimental replications reinforce this conclusion. When copper tubes with abrasive slurry are rotated by hand, minor misalignment quickly propagates into visible radial irregularity. Multiple operators, regardless of skill, cannot sustain a perfectly centered path over long depths. Only when mechanical guides, wooden collars, rigid frames, or vertical supports are introduced does the path straighten. With constraint, wobble is reduced, alignment improves, and circularity is maintained. The principle is simple. Lateral freedom produces deviation. Restriction produces stability. Such stability leaves subtle fingerprints. Tool pressure is concentrated along predictable paths. Groove width is consistent around the circumference. Depth variation is minimized. Minor taper may occur, but it correlates systematically with tool wear rather than random lateral drift. Even the interactions between copper and abrasive grains produce more uniform patterns because the relative motion is constrained. These are measurable consequences. They are the mechanical signature of stabilization. The fact that some ancient cores display these signatures raises a difficult question. How was stability achieved in a system assumed to be hand-driven? Loose copper tubes, driven by muscle alone, should not produce such consistent radial geometry. The evidence implies that some form of external support, constraint, or compensatory mechanism was used. This does not necessitate advanced machinery. It could involve simple devices, vertical posts, guides, or counter-supports that constrain lateral motion without altering the fundamental nature of the drill. But the implication remains. Human force alone is insufficient to account for what the stone preserves. Radial consistency also interacts with the groove pattern. A wobbling tool tends to produce grooves that vary in width and pitch. If the tube tilts, one side advances faster while the other lags. If it shifts, the helical path becomes irregular, sometimes overlapping, sometimes breaking apart. The cores in question, however, often show spirals of steady pitch combined with circular cross-sections. The two observations reinforce one another. Steady feed and radial stability are mutually dependent. Achieving one without the other is difficult. Achieving both under a purely hand-driven abrasive system is, by modern engineering standards, improbable. Even minor tool deformation complicates matters. Copper is ductile. Under load, it tends to flare or mushroom at the cutting edge. Left unconstrained, this deformation introduces radial inconsistency. Yet, in several cores, minimal deviation is observed despite the expected deformation under normal human-applied pressure. This suggests either that pressure was distributed in a way that limited tube flex or that the tool was supported laterally. Either way, the physical evidence points to stabilization beyond muscle control alone. Furthermore, radial symmetry is not merely a static measurement, it informs dynamics. A cylinder with uniform diameter distributes abrasive force evenly around the perimeter. Uneven walls would produce local stress concentrations, causing one side of the tube to cut more aggressively than the other. That would disrupt the spiral pattern, deepen grooves irregularly, and introduce asymmetry. The maintenance of both circularity and spiral regularity indicates that lateral deflection was minimized across the length of the core. The tool's motion was constrained dynamically as well as statically. The question of stabilization intersects with pressure as well. Maintaining radial symmetry requires not only lateral constraint, but also controlled downward force. If the operator applies uneven pressure, even a guided drill can drift. The walls would show localized deepening and tilting. The cause suggests that both rotational alignment and downward pressure were regulated to a degree beyond what casual hand application could achieve. The fingerprints of this regulation are subtle: uniform walls, consistent groove depth, and minimal deviation. But they are measurable and consistent across multiple examples. Finally, the presence of these fingerprints demands explanation within the known physics of the system. Loose copper tubes deform under load. Abrasive grains fracture unpredictably. Human operators cannot maintain perfect alignment over long durations, yet the evidence indicates that these limitations were mitigated. Constraint, whether mechanical, structural, or procedural, must have been applied. It could have been as simple as guiding posts, collars, or braces. It could have involved carefully tuned sequences of operator motion that minimized wobble. The exact method remains unknown, but the principle is clear. The stone itself demonstrates that tool stability was present, and tool stability requires intention. The near-perfect circularity observed in several cores cannot be dismissed as coincidence. It is the result of consistent forces applied along predictable paths. It is the silent record of stabilization, and it amplifies the underlying problem. Achieving such radial symmetry in combination with uniform helical grooves and substantial penetration pushes the limits of what a hand-driven copper tube with loose abrasive can accomplish. These fingerprints exist not as decoration, but as a record of mechanical constraint, and they demand explanation in the context of the known archaeological record. The next layer of complexity arises when one considers motion beyond simple rotation. Penetration into granite is fundamentally limited by contact mechanics. The abrasive grains must fracture the surface, and the tool must advance without deforming catastrophically. In hand-driven copper tube systems, this produces the constraints we have observed: slow advance, inconsistent grooves, and tool flex. But engineers have long recognized that adding a secondary motion, axial vibration or oscillation, changes the physics dramatically. In modern machining, ultrasonic drilling exemplifies this principle. A tool oscillates along its axis at frequencies far above human perception, often tens of thousands of cycles per second. Each oscillation generates micro-impacts between abrasive and stone, effectively fracturing the material with less net force. The tool need not push continuously to advance. The oscillatory energy itself contributes to penetration. The result is a dramatic increase in feed rate and efficiency, especially in hard, brittle materials like granite, quartz, or ceramic composites. Spiral patterns form naturally because each oscillation interacts with the rotational motion, producing helical abrasion without requiring constant high-magnitude pressure. The physics is compelling. Oscillation reduces the static friction at the interface, allows the abrasive grains to fracture more effectively, and mitigates tool deformation. In a modern context, this is precisely how feed rates comparable to those implied by the ancient cores are achieved. Machines that replicate such motions consistently produce deep, uniform spirals in granite with minimal lateral deviation. The combination of rotation and axial vibration enforces both radial symmetry and helical groove regularity, precisely the characteristics that puzzle engineers when examining ancient cores. Applied hypothetically to the Egyptian context, oscillation could, in theory, bridge the gap between slow stochastic abrasion and the observed feed rates. It provides a mechanism for controlled, sustained penetration without requiring superhuman force or unyielding mechanical constraint. Even modest oscillation, far less than ultrasonic levels, can enhance the efficiency of abrasive cutting by concentrating energy into repeated micro-impacts rather than continuous pressure. This reduces tool deformation, distributes wear more evenly, and can produce grooves that appear remarkably regular over tens of centimeters. Yet here lies the dilemma. No archaeological evidence exists for vibration-assisted devices in ancient Egypt. There are no remnants of resonating frames, oscillating weights, or mechanical actuators that could generate axial vibration at meaningful frequencies. Egyptian metalworking and mechanical knowledge, while advanced in other domains, shows no precedent for oscillatory drilling mechanisms. Invoking oscillation as an explanatory tool, therefore, is seductive mathematically, but speculative historically. It resolves the engineering paradox on paper, but introduces a narrative gap, a technology for which there is no physical record. This raises a philosophical tension. Is oscillation an explanation grounded in the physics of the problem, or is it an evasion designed to preserve the assumption that hand-driven copper tube drilling sufficed? On one hand, it is undeniable that oscillatory motion would change everything. The physics supports the concept. Models incorporating vibration show that penetration rates can increase by orders of magnitude, radial symmetry is stabilized, and helical grooves form naturally. On the other hand, invoking oscillation without evidence risks substituting a hypothetical mechanism for the empirical constraints the cause present. It does not answer the question of how the ancients actually achieved the results. It simply demonstrates that such results are possible under different physical conditions. Modern ultrasonic drilling also illustrates the principle that feed rate is not simply a function of tool hardness or human strength. It is a function of energy input, motion type, and interface dynamics. Copper is weak, human arms fatigue, hand pressure is inconsistent. Introduce oscillation, and the apparent mechanical limits dissolve. The grains fracture more efficiently, the copper deforms less, and the spiral can form with minimal wobble. This shows that the constraints identified in prior analysis, pressure, tool stability, abrasive behavior, are not absolute. They can be mitigated if additional degrees of freedom in motion are present. Yet this insight does not solve the historical puzzle. The Egyptian cores were not produced with ultrasonic technology. If oscillation is invoked, it must be justified within the technological framework available at the time. Could simpler forms of vibration have been applied, perhaps by percussive tapping, rhythmic pulleys, or manual jarring of the drill assembly? Even minor repeated axial impacts would reduce the normal force required and improve abrasive effectiveness. But there is no direct evidence for such methods. Archaeologists have found no traces of mechanical jigs capable of generating controlled oscillation at the necessary scale. The debate then turns on what is physically necessary versus what is historically documented. From a purely engineering perspective, oscillation explains many otherwise anomalous features: high feed rate, spiral regularity, and radial symmetry. From a historical perspective, it is conjecture. Its invocation illuminates the physics, but does not account for the archaeological record. This tension forces a distinction between possible and demonstrable. Oscillation is possible. It works. It would solve the engineering problem. But possible is not evidence. Without corroborating artifacts, drawings, or textual descriptions, it remains a theoretical intervention, a thought experiment that demonstrates feasibility rather than reality. The cores themselves do not speak to oscillation. They record material removal, depth, pitch, radial consistency, surface finish. Any oscillatory process that might have contributed would leave indirect signatures, subtle micro-chipping patterns, or perhaps tool wear anomalies. To date, these have not been definitively identified. The fingerprints of oscillation, if they exist, remain indistinct. The question lingers: are we justified in using oscillation to reconcile the measurable engineering fact with assumed capability? Or are we substituting a modern solution for an ancient enigma? The physics is undeniable. Oscillation changes everything. But the historical record remains silent. In confronting this tension, we are reminded that engineering insight and archaeological evidence do not always converge. The stone preserves a record of action and outcome, but not intent or mechanism. Oscillation illuminates what could have been achieved under different conditions, and in doing so, highlights just how challenging the observed feat was under hand-driven assumptions. It frames the problem, not the solution. The ancient cores demand an explanation that satisfies both the laws of physics and the historical context. Oscillation demonstrates that the laws of physics can accommodate the observed penetration rates and spiral regularity. What remains uncertain is whether the Egyptians leveraged any mechanism, simple or complex, that approximated this principle, or whether the apparent efficiency is encoded differently than we imagine. The difference between explanation and evasion is subtle yet critical. One respects both measurement and evidence. The other preserves plausibility at the cost of historical rigor. The first thing to grasp is what the granite cores actually communicate. They do not speak in words. They do not carry inscriptions that tell a story. They do not encode names, dates, or motives. The stone is silent on identity. It offers no biography of the hand, the artisan, or the team that set the drill spinning. No hieroglyph inscribed into the granite declares authorship. Archaeology provides context, but the stone itself does not. Nor does it explain purpose. The cylinders could be functional, experimental, symbolic, or structural. They could be remnants of trials or elements of monumental construction. They could represent a fleeting impulse or the culmination of a long tradition of craft. The granite cores do not indicate whether they were ends in themselves or means to an architectural or ritual objective. The why remains unrecorded, invisible to measurement. Most strikingly, the stones do not disclose the source of energy that produced the observed effects. They do not tell us whether a single operator bore the load or whether a team applied coordinated force. They do not describe the existence of mechanical aids, guides, weights, or oscillatory devices. The measurable feed rates and spiral geometries imply that energy was applied in a regulated fashion, but the granite remains mute on how that regulation was achieved. It is a ledger of result, not method. What the stones do provide is quantitative evidence. They record geometry, diameters, taper, depth, pitch, radial symmetry. They record patterns of wear and deformation. They encode interaction between tool and material. In other words, the granite is a witness to physics. It measures outcomes. It does not speculate on human intention. It does not moralize or mystify. It simply records that, under some combination of force, motion, and constraint, material was removed in ways that are measurable, reproducible in principle, and at times anomalous when compared with assumptions about known techniques. This is a subtle but critical distinction. Human imagination tends to fill gaps with stories. We instinctively ask who, why, and how, because we crave narrative. But in this case, the stone refuses the narrative. It offers only metrics. The spiral pitch, the taper, the groove depth, they are data. They do not explain themselves, but they do not lie. They quantify the interaction, and in doing so, they expose the tension between observation and assumption. That tension is sharpened by measurement. When engineers calculate feed per rotation, assess required pressure, or evaluate tool stability, they confront discrepancies. The numbers can be reproduced in equations, compared against material properties, and framed in mechanical models. But none of this tells us whether humans, weights, guides, or other interventions were used. The numbers do not imply intention, only constraint. They define what must have occurred mechanically, but not who or why it occurred. The evidence, in its impartiality, is almost accusatory. It forces us to confront limitations in our understanding. When replication fails, when material science explains some features but not others, the stone is unmoved. It does not apologize. It does not offer excuses. It simply preserves what happened, a copper tool or series of copper tools interacting with granite in ways that at times exceed what we assume to be the technological baseline.
By focusing on what the stones do not say, we clarify the scope of inquiry. Speculation about identity, purpose, or power source can enrich the narrative, but it is not evidence. The only secure ground is what can be measured and inferred mechanically. Spiral pitch, radial symmetry, groove depth and taper, these are observable. Pressure, tool wear, and feed rate are calculable. The interaction is tangible. Everything else remains conjecture. This distinction also underscores the enduring paradox. The anomaly is not mystical, it is measurable. We can quantify the constraints and limits of hand-driven copper tubes. We can calculate the pressures required to fracture granite at the observed rates. We can assess radial symmetry and helical consistency, and yet the data refuses to reconcile easily with the simplest models. The stones measure, our models struggle. That is the essence of the contradiction.
Acknowledging what the evidence does not say also guards against error. It prevents us from projecting modern assumptions or narrative desires onto the stone. We cannot claim certainty about tools, teams, or techniques beyond what the physics and surviving archaeology permit. We cannot assume genius, innovation, or ritual intent. Those remain human interpretations. The stone, however, provides immutable quantities: depth, diameter, pitch, symmetry. It defines the mechanical boundary conditions. Within those boundaries, we must work. Outside them, speculation begins. Ultimately, the stones operate as impartial auditors. They do not reward imaginative storytelling. They do not punish analytical rigor. They simply record outcomes, leaving the observer to reconcile measurement with expectation. In doing so, they expose the narrow corridor between what is mechanically possible and what has been historically assumed. That corridor is both tantalizing and exacting. It is narrow because granite, copper, and human strength are quantifiable. It is tantalizing because within that corridor lies evidence of achievement that, by simple extrapolation of known techniques, appears improbable. The stones accuse no one. They make no moral or cultural claims. They do not contextualize human labor, nor comment on ingenuity or skill. They do not even offer reassurance. They do not tell us that the result is expected, safe, or explainable. They merely measure. And that measurement persists over millennia, indifferent to interpretation, immune to bias, and silently insistent. The interaction happened, it is quantifiable, and it challenges assumptions about technological limits. It is in this context that the next questions emerge. Having established what the cores record and what they withhold, the focus must turn to how energy, motion, and constraint interacted to produce the observed outcomes. The stones do not say how, they do say what happened. Every subsequent analysis must remain grounded in that fundamental distinction. The stone speaks in measurement, not in story. The rest, identity, purpose, method, is speculation, and in that silence lies both the challenge and the invitation. Measurement alone frames the paradox. It forces us to confront the limits of what is known and what can be inferred. It leaves us with a simple, unambiguous question. Given the observable features of the cores, what combinations of force, rotation, and constraint could have produced them? The answer cannot rely on conjecture. It must respect the immutable record preserved in the granite. The cores, in their silence, offer a kind of austere clarity. They do not whisper secrets. They do not hint at genius or ritual. They only measure. And it is precisely that impartial numerical truth that drives inquiry forward, compelling us to reconcile observed effect with assumed capability. The simplest hypothesis is often the least glamorous. Perhaps we have been overinterpreting what the stone actually records. The grooves, after all, are small, subtle, and subject to millennia of environmental and human influence. Abrasive marks can overlap, merge, and shift. A series of irregular scratches, if viewed from the right angle, might resemble a continuous helix. What appears deliberate may in fact be coincidental, the product of repeated stochastic abrasion rather than sustained feed. Erosion complicates the picture further. Granite is hard but not impervious. Centuries of wind, sand, and temperature variation can subtly widen grooves, deepen depressions, or exaggerate apparent spacing. Measurements taken today may overstate the regularity or steepness of the spiral. What seems like a high feed rate per revolution could be, in part, a post-depositional artifact. The cumulative effect of weathering may create an illusion of deliberate machining where none existed. Even experimental replication carries risk of bias. Engineers approach these cores with the tools and logic of modern machining: feed per revolution, pitch, tool wear. It is natural to read those parameters into the stone, assuming that a spiral implies controlled motion. But perhaps we are imposing a framework that did not apply. Pre-industrial artisans did not think in revolutions per inch. Their priorities may have been functional, symbolic, or procedural in ways that leave patterns resembling but not equivalent to engineered helical grooves. The notion of misinterpretation also accounts for variation among cores. Some exhibit remarkable regularity, while others are irregular or incomplete. If the apparent anomaly is partially a perceptual artifact, this would reconcile why certain examples provoke astonishment while others do not. It would also explain why replication experiments consistently fail to produce perfect matches. The features being measured are, to some extent, products of cumulative noise, not precise design. Skepticism, however, cuts both ways. Misinterpretation is plausible, but it cannot erase the undeniable facts. The cores do possess measurable spiral geometry, radial consistency, and feed indicators that resist simple explanation. Even accounting for erosion and coincidence, the degree of uniformity in several specimens remains unusual. It is not sufficient to claim that all observations are illusions. The tension persists because some aspects of the pattern are quantifiable, repeatable, and inconsistent with naive expectations of loose, human-powered abrasive drilling. This duality is critical. On one hand, misinterpretation offers a conservative explanation. The anomalies are perceptual or environmental. On the other hand, measured parameters, groove spacing, depth, and radial stability demand a mechanical account. One cannot simply dismiss the numerical data in favor of perception alone. The evidence is both stubborn and ambiguous. It invites rigor and encourages humility. Thus, misinterpretation is a hypothesis, not a solution. It serves as a counterweight to more imaginative proposals that invoke unseen mechanical aids, oscillation, or complex procedures. It reminds us that cognitive bias, environmental change, and measurement error can amplify apparent anomalies. But it also forces a careful separation of what is observable from what is assumed. The stones are precise in what they encode. Human interpretation is where uncertainty enters. In practical terms, this means that each measurement must be scrutinized critically. Spiral pitch, groove depth, radial alignment, all must be assessed in light of potential exaggeration or artifact. Cross-sectional analysis, microscopic wear patterns, and comparison across multiple cores can reveal whether apparent regularity is genuine or illusory. Only by combining quantitative measurement with controlled skepticism can the full scope of the anomaly be understood. Ultimately, misinterpretation highlights the epistemological challenge at the heart of the problem. Measurement and observation are not the same as understanding. The cores are silent witnesses. They offer numbers and patterns, but they do not validate the conclusions drawn from them. To reconcile the measured spiral features with plausible technique, one must remain alert to both mechanical constraints and perceptual biases. Skepticism, in this sense, is a methodological tool. It prevents us from jumping to conclusions about technological impossibility or lost ingenuity. It reminds us that the simplest explanation, cumulative, overlapping, eroded marks, must be considered alongside more complex mechanical accounts. The paradox does not vanish, it is reframed, constrained by what the evidence actually allows. Even in this tempered framework, the core question remains. What combination of force, motion, and constraint produce the observed features? Could randomness and erosion truly simulate consistent spiral feed? Or do the data demand some form of mechanical assistance, subtle as it may have been? Misinterpretation does not answer these questions, it sharpens them. It forces a disciplined assessment of what is truly anomalous, what is likely, and what remains unexplained. In the end, the hypothesis of misreading serves less as a solution than as a lens. It clarifies the boundary between measurement and interpretation, reminding us that the stones themselves are impartial recorders, while humans supply narrative, expectation, and logic. Whether the grooves represent deliberate engineering or the cumulative effect of repeated abrasion, the measurable facts remain. The patterns exist, they are quantifiable, and they invite both awe and rigorous inquiry. It is within this tension between possible misinterpretation and mechanical reality that the subsequent analysis must operate. The anomaly persists, the data is persistent, and the search for explanation continues. The temptation in examining these cores is to reach for extraordinary explanations. Some might imagine lost civilizations, secret technologies, or interventions beyond the archaeological record. Such notions are seductive. They promise closure, a tidy resolution to the cognitive tension that arises when measured effect exceeds assumed capability. But the evidence does not support such narratives. The stones themselves speak only of measurable interaction between tool and stone. They do not require myth, and invoking it obscures the very discipline we are trying to apply. Engineering is fundamentally about inference. We observe outcomes, identify constraints, and reconstruct processes consistent with physics, materials, and known mechanics. In the case of the granite cores, the measured pitch of the spirals, the feed per revolution, the radial symmetry, and the taper provide a set of boundary conditions. Any proposed process, hand-driven copper tube, oscillatory mechanism, or otherwise, must satisfy these constraints. If it does not, the inference fails. This is the essential discipline of engineering. Measurable outcomes define permissible mechanisms. Boundary conditions are critical. In physics and mechanical design, ignoring them produces error. Feed rate is not a suggestion, it is a parameter dictated by geometry and material behavior. Radial stability is not aesthetic, it is a signature of tool constraint. Pressure is not abstract, it is quantifiable, limited by both tool yield and human strength. When assumptions about these boundaries are wrong, the conclusions drawn from the model become unreliable, no matter how elegant the narrative. This is why replication experiments are so revealing. They expose the discrepancy between theoretical feasibility and measured effect, highlighting where assumptions about tool behavior and applied force fail. Humility in engineering does not mean surrender. It does not require abandoning inquiry. It means respecting constraints, acknowledging uncertainty, and letting the data dictate the parameters of what is plausible. The granite cores do not demand myth, they demand rigorous attention to measurable facts. The anomaly is not in what humans can imagine, it is in what the numbers indicate about material interaction, tool behavior, and mechanical limits. Humility recognizes that these numbers may defy intuitive expectations without requiring supernatural explanation. Consider the difference between possibility and plausibility. It is possible that a human with a copper tube and sand could remove a core from granite. Experiments confirm this. But the plausibility of achieving the observed feed rates, spiral consistency, and radial symmetry under purely hand-driven conditions is far lower. Engineering inference makes this distinction visible. It forces us to quantify limits, assess material behavior, and compare theoretical maximums against measured outcomes. Only then can we identify the real discrepancy. What is physically recorded does not align with what simple reconstructions predict. This is the core of the anomaly. It is not mystical. It is not alien or lost. It is a mismatch between measured effect and assumed mechanism. Engineers face such challenges constantly. Systems behave differently than expected when a variable is misunderstood, a boundary condition overlooked, or an interaction between components underestimated. The granite cores illustrate the same principle in a historical context. Misjudging pressure, ignoring tool deflection, or underestimating the impact of material heterogeneity leads to models that cannot reproduce observed patterns. The discrepancy is measurable, not mythical. History does not require miracles. It requires careful attention to constraints. Archaeology provides context, but it is engineering that interrogates feasibility. We can ask, how much pressure can a copper tube sustain? How consistent can human-powered rotation be? What is the effect of abrasive grain size, slurry viscosity, and cumulative tool wear? Each question is grounded in physics and material science, not speculation. Answers provide a framework for understanding what is plausible, even if full replication remains elusive. Engineering inference also illuminates the gaps. Where simple models fail, the anomaly becomes instructive. It teaches about the limits of assumed techniques, the sensitivity of processes to boundary conditions, and the subtleties that may have been mastered by ancient practitioners. Perhaps they developed mechanical aids, sequencing methods, or procedural knowledge that we have not reconstructed. Perhaps skill, patience, and iterative adjustment allowed higher than expected performance. The numbers define the challenge. The solution, historical or modern, is constrained by them. Ignoring the numbers is tempting, especially when they suggest improbability. It is easier to attribute exceptional results to mystery than to confront the uncomfortable reality that simple models may be incomplete. Yet, this is precisely where humility matters. A rigorous approach respects the data. It acknowledges that the observed effect may exceed what our current models predict, without leaping to fantastical explanations. It maintains the discipline that separates engineering inference from storytelling, measurement from mythology. The cores, in this sense, become instructive beyond their immediate context. They demonstrate how observable outcomes encode mechanical information. They remind us that engineering insight relies on careful interpretation of measurable parameters, that each variable, feed rate, radial stability, tool deformation, is meaningful, and that apparent contradictions are opportunities for refinement rather than invitations to myth. In examining them, we learn to ask better questions, to model more carefully, and to remain skeptical of assumptions that are convenient rather than justified. Finally, engineering without myth restores perspective. It allows the paradox to remain both puzzling and tractable. We recognize that the cores challenge assumptions, that they exceed the performance predicted by naive reconstructions, and that our understanding of historical technique may be incomplete. But we also recognize that this is a solvable problem within the laws of physics and material behavior. The mystery is intellectual, not supernatural. It is the kind of challenge that sharpens inquiry, requiring measurement, modeling, and disciplined interpretation. Humility does not mean ignoring numbers. It means letting the numbers define the boundary of plausibility, guiding hypotheses, and framing questions. The anomaly is not diminished by restraint, it is clarified. By removing myth, we are left with measurable tension between observed effect and assumed capability. That tension, precisely because it is measurable, is where knowledge grows. The lesson extends beyond granite, copper, and sand. It is a lesson in thinking rigorously about the intersection of observation, theory, and assumption. Boundary conditions matter. Mechanical limits are real. Measurement is unambiguous. And when models fail, the failure is as informative as the success. In the case of the Egyptian cores, this principle transforms the paradox from a source of speculation into a framework for disciplined inquiry, revealing the challenge, the constraints, and the paths for understanding that remain open. The paradox is not absolute. It exists in a defined, measurable corridor between what is known and what can be reliably demonstrated. Experimental archaeology confirms that copper tubes, sand abrasives, and human labor are capable of penetrating granite. Cores can be extracted, material is removed. The basic process is within the realm of possibility. There is no mystery in principle. Yet when we examine the grooves quantitatively, a different picture emerges. The pitch, feed rate, radial symmetry, and surface finish observed in certain Egyptian cores remain beyond what has been reliably reproduced. The measurable parameters of some ancient examples exceed the limits of hand-driven replication. Even with careful control, guides, and consistent pressure, modern attempts struggle to generate the same helical regularity and penetration per rotation. The discrepancy is small in absolute terms, but large in relative terms. A factor of 2, 3, sometimes more in feed per revolution, with circularity maintained over tens of centimeters. This gap between known capability and observed effect is narrow but telling. It is not a chasm suggesting impossibility. It is a tight corridor where physics, tool behavior, material response, and procedural knowledge intersect. Every parameter, abrasive efficiency, tool stiffness, operator fatigue, granite hardness, constrains what is achievable. Within those constraints, the measured cores sit just outside what has been confirmed by replication. That just outside is where inquiry focuses. It is neither myth nor miracle, merely the edge of current understanding. The significance of the gap is methodological. Science advances not by cataloging what is easy, but by probing the boundary between theory and observation. Here, the measured spiral patterns and feed rates define a target. The failure to reproduce them precisely does not indict human ingenuity. It highlights the sensitivity of the system to boundary conditions. Minor changes in pressure, alignment, or abrasive behavior produce large deviations. The narrowness of the corridor shows how precisely controlled the process must have been, whether by tool, procedure, or operator. It is instructive to compare this to other engineering challenges. Many feats in historical technology, catapults, water clocks, masonry precision, were achievable in principle but demanded skill, iteration, and incremental refinement. Observation of the result alone does not tell us the stepwise method, only the final effect. Similarly, the cores represent outcomes, not manuals. The narrow gap emphasizes that the ancients' achievements, while physically plausible, were executed with attention to detail that pushes the limits of what naive replication can achieve. Importantly, the gap is a research question, not a verdict. It is an invitation to investigate, model, and experiment. Which variables most influence groove pitch and radial symmetry? How does pressure distribution, tool stability, or abrasive choice alter performance? Can small innovations, jigs, supports, coordinated operator sequences, bring replication within measured parameters? These are questions that modern engineering can explore, guided by the immutable data preserved in the stone. The narrowness of the gap also reframes the anomaly. The cores are not evidence of technological impossibility, lost knowledge, or miracle. They are evidence that precise interaction with difficult materials produces outcomes sensitive to many factors. Slight deviations in any factor, rotation speed, pressure, tube rigidity, abrasive size, can yield dramatically different results. The ancient examples sit in a zone where multiple factors aligned optimally. The gap highlights how demanding those conditions were and why replication is difficult. This framing transforms the paradox into a productive challenge. The focus shifts from speculation to measurable mechanics. How do the observed features emerge under controlled conditions? What combinations of rotation, feed, pressure, and constraint could produce uniform helical grooves in granite using copper and abrasive? By reframing the problem in terms of parameters and boundary conditions, the anomaly becomes a laboratory question, not a philosophical or mystical one. Here, science lives. Not in certainty, not in conjecture, but in the tension between what is measured and what can be reproduced. The narrow gap is precisely the place where inquiry is active. It is the region where hypotheses are tested, models are refined, and understanding incrementally expands. Unlike myth or conjecture, it is resolvable in principle. Additional experiments, careful modeling, and precise measurement can illuminate the conditions that produce the cause. In essence, the cores are a challenge wrapped in granite. They quantify a process that is within the laws of physics, yet outside the envelope of our simplest reconstruction. That narrow space between known capability and measured effect is not discouraging. It is defining. It identifies exactly where attention must be focused. It highlights the sensitivity of mechanical interaction and the importance of disciplined, quantitative inquiry. The contradiction is real, measurable, and bounded. It does not imply impossibility, it implies opportunity. It reminds us that science thrives not where answers are easy, but where they are incomplete. The Egyptian cores, with their helical grooves, radial stability, and feed parameters, sit at that boundary. They demand rigor, curiosity, and experimental discipline. They show that the limits of known techniques and the measured outcomes are not coincident, but close enough to challenge understanding, but not so far as to defy it. Unanswered questions are where science actually lives. The granite does not cheat. It records what happened, leaving the investigator to reconcile observation with model, measurement with mechanism. The narrow gap between what can be reproduced and what is observed is a corridor of possibility. It is a laboratory for the mind, a space where engineering, archaeology, and materials science intersect. Within this corridor, understanding advances, hypotheses are tested, and the measurable anomaly becomes the engine of inquiry itself. The cores, in their enduring precision, teach a vital lesson. Science is not about certainty. It is about boundary conditions, constraints, and the persistent pursuit of what is possible within them. The narrow gap is not a failure. It is the heart of investigation, and in that precise, defined, and stubbornly persistent space, knowledge grows, one experiment, one calculation, one observation at a time. The granite cores have survived millennia not because of legend or law, but because they are durable records of interaction, tool against stone, force against resistance, rotation against material. They bear no inscription of intent, no confession of method, no clue of purpose beyond what is physically measurable. And yet within their silence they speak with a clarity that demands attention, precision, and humility. They do not ask for belief. They ask for rigor. To understand these cores is to confront the limits of modern certainty. We may approach them armed with engineering theory, replication experiments, and centuries of accumulated knowledge about tools and materials. Yet the stone continually reminds us that measurement is both the starting point and the final arbiter. Pitch, radial symmetry, groove depth, and feed per revolution are not opinions. They are quantitative markers of what happened. Any hypothesis that ignores these numbers, that prioritizes narrative over data, risks collapse under scrutiny. The stone measures, we interpret. The discipline is ours. Replication is equally exacting. Attempts to reproduce the cores with hand-driven copper tubes and abrasive slurry consistently fail to meet the combined standards of pitch, symmetry, and depth recorded in the ancient examples. Small variations in pressure, alignment, or operator technique produce deviations that accumulate rapidly over tens of centimeters of granite. This is not a failing of imagination. It is a reflection of the physics embedded in the material. The stone sets the standard, and each experiment is a negotiation with reality, a test of whether assumptions match measurable outcome. The cores also expose the subtleties that can be overlooked when certainty becomes habitual. Hand-waving about possible methods is insufficient. Calculations of feed rate, pressure requirements, and tool deformation reveal discrepancies that are uncomfortable precisely because they are precise. The anomaly is not vague, it is quantifiable. It does not admit to metaphor, it does not bend to narrative. It exists as a boundary, defined by the physical interaction between copper, sand, human force, and granite's resistance. And it is in that defined boundary that true understanding must be sought. Modern tools of measurement, calipers, profilometers, 3D scanning, reveal discrepancies invisible to the naked eye. Groove pitch that seems regular by glance may, under precise inspection, encode feed rates orders of magnitude beyond what a bow-driven copper tube can sustain consistently. Radial symmetry that appears adequate may, under microscopic measurement, display minimal but consequential deviations. These differences matter. They are the language of the stone, and they demand that we listen with instruments as well as intellect. Yet even as we measure, the stones also teach restraint. They remind us that absence of evidence is not evidence of impossibility. The question is not whether humans were incapable of producing these features, but whether our assumptions about methodology are incomplete. Simple tools may have been supplemented by clever procedural innovations, jigs, supports, sequencing, team coordination. The stone does not reveal these directly, but it encodes the mechanical consequences. Every groove, every spiral, every centimeter of radial stability is a footprint of applied principle, even if the principle itself is obscured by time. This interplay of measurement and inference is where science truly operates. The stone sets the parameters. Theory proposes possibilities. Experiment tests feasibility. When gaps persist, when measured outcome exceeds expectation, certainty falters. And it is precisely in that faltering that understanding deepens. The mystery is not an appeal to the exotic or the unknowable. It is an encounter with the limits of method, assumption, and observation. The stones also remind us of epistemic humility. We often regard modern knowledge as complete, precise, and sufficient. Yet when a caliper measures an ancient core, we are forced to admit that our models, however sophisticated, may overlook critical variables. Feed rates exceed human-powered expectations. Radial symmetry challenges assumptions about tool wobble. Spiral pitch defies replication. These are not minor inconveniences. They are tangible indications that even disciplined knowledge can underestimate complexity. The stone does not reproach, but it is insistent. Measurement is final. In this way, the cores demand a kind of intellectual honesty. They ask us to resist the comfort of dismissal, the urge to claim coincidence, erosion, or misinterpretation as the full answer. They ask us also to resist fantasy, the lure of lost technologies, miraculous techniques, or unseen machinery. The true challenge is to reconcile measurable reality with plausible historical method. The stone does not provide the answer. It defines the problem. It frames the challenge, leaving the investigator to bridge observation and explanation with rigor and care. There is also a moral dimension, subtle yet real, in this insistence on measurement. The cores confront us with the consequences of assumption unchecked. They ask whether we are disciplined enough to let data guide interpretation, even when the numbers whisper something inconvenient. In this case, the whisper is that the observed feed rates, spiral geometries, and radial stability do not comfortably fit the simplest model of hand-driven copper tube drilling. The whisper is precise, quantitative, and resolute. To ignore it is to privilege narrative over fact. The lesson extends beyond the specific case of Egyptian cores. It is a principle for all inquiry where data meets expectation. Measurement does not always align with assumption. Engineering inference can be challenged by unexpected outcomes. Material interaction can defy naive replication. And in every instance, the correct response is not to invent story, but to interrogate method, refine model, and pursue disciplined experiment. This is where science lives, in the tension between what is observed and what is presumed. Ultimately, the stones leave us with a singular task: to measure carefully, replicate rigorously, and interpret faithfully. They ask us to accept that ancient human action can produce outcomes that stretch our assumptions without requiring the fantastic. They ask us to confront the limits of our models, the narrow corridors of possibility, and the precision of nature preserved in stone. And they ask us, above all, to let the numbers speak, even when those numbers are inconvenient, counterintuitive, or resistant to our expectations. In listening to these silent witnesses, we learn a broader lesson about certainty, humility, and the practice of inquiry. The stones do not demand admiration, speculation, or belief. They demand discipline. They demand engagement with measurement. They demand that we respect the truth embedded in material consequence. And in this discipline, the true mystery of the granite cores is revealed, not in the distant past, not in hidden technologies, but in the persistent challenge they present to anyone willing to let evidence lead, to follow the caliper rather than imagination, and to recognize that the path to understanding lies not in fantasy, but in faithful attention to what is measurable. The final question, then, is ours. Will we be disciplined enough to listen, to measure, to replicate, and to admit when reality exceeds our expectation? The stone does not answer. It waits, it records, it measures, and in doing so it challenges every assumption, every model, and every assertion of certainty we bring to it. It asks nothing more and nothing less. Let the numbers speak. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.